So I wanted to use this as an example of relative motion. So as you see, this person is running on the train here, which isn't a smart idea, but running on this train and they're not getting anywhere, right? The train is moving one direction and they're moving the other. Again, I don't recommend doing this, but it's a good example of how relative motion works. This person's running on the train. So the train is moving this direction, and we'll call that VA is equal to 10 miles per hour. Now this idiot up here is running the opposite direction, and that is the velocity of B with respect to A. And let's say that person can run 10 miles per hour. That's the top speed of this person running on the train. So from the observer that's on the ground here, the velocity of this person, B, right, is the velocity of A plus the velocity of B with respect to A. So here we have VA, which we can call negative 10, since it's to the left, right, the negative x direction. And then we have the velocity of B with respect to A, 10 miles an hour positive, all right? And that is equal to 0. So from an observer on the ground, it appears that the person's not moving at all, right? A 0 mile an hour velocity. We just looked at a 1D example of a person running on a train, but this also applies to vectors. So we can write things like the velocity of B as a vector is equal to the velocity of A plus the velocity of B with respect to A. So we're adding vectors here, tip to tail, to come out with the vector B. And likewise, we can also do this with acceleration. Acceleration of B equals the acceleration of A plus the acceleration of B with respect to A. We have a quick example here of a train and an automobile. And the velocity of the automobile is moving at 45 degrees at 45 miles an hour, right here. And the velocity of the train is 60 miles an hour horizontal here. And we're looking for the velocity of the train with respect to the automobile. All right, so let's write out the equation. We have the velocity of the train is equal to the velocity of the automobile plus the velocity of the train with respect to the automobile. So make sure you get this equation right. The bottom half have to correspond here, and the top here corresponds with the left-hand side. So you must get this equation right first. So the velocity of the train here is horizontal at 60 miles an hour. So that's just 60 in the I direction. And the velocity of A is then, well, it's 45 miles per hour cosine 45 degrees in the I direction, and then plus 45 sine 45 degrees in the J direction, okay? And now we're looking for the velocity of the train with respect to the automobile. So subtracting these from the other side, or to the other side, subtracting these, we get the velocity of the train with respect to the automobile is equal to 28.2 in the I direction minus 31.8 in the J direction. Okay, so that is the velocity of the train with respect to the automobile, but we also like to know what is the magnitude of this. So if we take the sum of the squares here and take the square root, that we get the magnitude of this velocity comes out to be 42.5 miles per hour. All right, miles per hour there. And then we can also find the angle of this vector, where the tangent of theta, right? If we draw this out, all right, we have 28.2 in this direction, and then downward we have 31.8, and we have, this is our theta here. So we have, well, we could just put a positive here. 31.8 divided by 28.2, theta comes out to be 48.5 degrees. And we must note that that's from right? That's this angle here.